Okay, we're going to continue on with our blue and yellow tiles in a bag, but we're going to turn it into a game. Suppose you play a game in which player 1 wins if they match, either a blue-blue or yellow-yellow, and player 2 wins if the tiles are different, blue-yellow or yellow-blue. Each of these events is considered non-overlapping. Because the game can result in one of the four, but not more than one at a time. So we've got our definition here of two non-overlapping events. And to find the probability that A or B occurs is the probability of A plus the probability of B. And note this can be extended to any number. So if you're looking at four non-overlapping events, then you can do it with that. Okay, so let's do method 1. And we want to determine if the game is fair. Okay, so does it matter which method you use? We're going to use all the probabilities found in number 3 to answer these questions. Okay, so we're going to start with replacement, with them being independent events. Okay. All right, let's calculate the probability that player 1 wins. Okay, well, the probability that player 1 wins is the probability of blue-blue or yellow-yellow. If I look back on my sheet, then I find that the probability of blue-blue is 1/4. The probability of yellow-yellow is 1/4. So that becomes 2/4 or 1/2. Okay. If we calculate the probability that player 2 wins, okay, well, the probability that player 2 wins is the probability of blue-yellow or yellow-blue, which is 1/4 plus 1/4. Again, that's 2/4 or 1/2. Okay. Now, let's do it without replacement. This is where once you've pulled a tile, it is taken away from the bag. Okay, and we're going to again use the probabilities from the page before. I'm not going to flip back and forth. Player 1 wins is the probability of blue-blue or yellow-yellow. Well, the probability of blue-blue is 1/6. The probability of yellow-yellow is 1/6. So that becomes 2/6 or 1/3. The probability that player 2 wins, so we have player 2. So the probability that player 2 wins is the probability of blue-yellow or yellow-blue, which is 1/3 plus 1/3, which is 2/3. Okay, is the game fair? Well, we have to compare the probabilities. So with replacement, it is fair. The probability for each player is 1/2. Without replacement, excuse me. It is not fair. Poor player A only has a 1/3 probability of winning. Player B has 2/3. So you can see that the probabilities, whether they are independent or dependent events, change, and it can turn a fair game into a not fair game, or vice versa. Okay, let's consider this experiment. We're going to draw a card from a standard deck of 52 cards, put it back in the deck, and drawing another card. Okay. All right, so what are we going to do here? We are going to draw a card, put it back in the deck, and then draw another card. These are independent events because we are replacing it. This is with replacement. Okay. So what is the probability of drawing 2 aces in a row? Okay. So what we're looking for is the probability of an ace and an ace, which is the probability of an ace times the probability of an ace. Okay. They are independent events, so what happens here has no bearing on what happens here. Okay, well, there are 4 ways to draw an ace out of the 52 cards. Since the card was replaced, there are still going to be 4 possibilities out of 52 cards. If I do the multiplication, that's 16 over 2,704, or 1 over 169. Okay, let's try again. It's time for a snack. A bag of M&Ms. They have 6 red, 5 yellow, 2 green, 1 blue, and 4 purples. You select an M&M from the bag, eat it, and select another one. Okay. All right, now what is different about this one is once you select the M&M, you eat it, which makes these dependent events because it is without replacement. Okay. Now, we've talked about this many, many times before about how visual I am. If I'm doing a thing like this, I'm going to draw my M&Ms. So I'm going to draw 6 red. I'm going to draw 5 yellow. I'm going to draw 2 green. I'm going to draw 1 blue. And I am going to draw 4 purple. Okay. Okay, and the first thing I'm going to do is total up. If I'm going to find some probabilities, then I need to know what my total outcomes are. Which means if I'm drawing in a bag, this gives me 18 equally likely outcomes. Okay, I can get any one of the 18. Okay, so let's find the probability of drawing a red followed by a green. Okay, now to write this, this is going to be the probability of a red times the probability of a green given that you've already drawn a red. So what does that mean? Well, the probability of a red on my first draw, there are 1, 2, 3, 4, 5, 6 out of the possible 18. But now let's look at the probability of drawing a green. We have to consider that one of these is gone, which means we not only no longer have 18 equally likely outcomes, there are only 17, because you've eaten one of the M&Ms, so there are 17 left in the bag. There are 2 green out of those 17 possibilities. That gives us 12 out of 306, which becomes 2 out of 51. Okay. All right, so what is the probability of drawing a red, then a blue, and then we get a purple one? And remember, we're eating these. Okay, so we need to find the probability of a blue times the probability, probability of a red, excuse me. The probability of a blue, given that you've already drawn a red, times the probability of a purple, given blue given red. Okay, so what's going to happen on each of these is the number of M&Ms in the bag are changing. It's going down by 1 because you're eating them. Okay, so the probability of a red. If you start out, there are 6 out of 18. Okay, now the probability of a blue. Well, there are no longer 18, there are only 17, but there are 2 blues. Okay, so now one of these and one of these are gone. So now there are only 16 left in the bag, and there are 4 purple out of that 16. So when you multiply these together, you end up with 24 divided by 4896, which is 1 out of 204. Okay, what is the probability of drawing 2 yellow M&Ms in a row? Remember, you're eating them. So we want to find the probability of a yellow on the first one times the probability of a yellow given we've already done a yellow. Okay. Well, the probability of a yellow on the first draw, there are 5 yellow out of 18 possible outcomes, and now one of those is gone. So now there are only 4 yellow left out of the 17 remaining M&Ms. And what you get when you multiply this is 20 divided by 306, which is 10 over 153. Okay. All right, what is the probability of drawing 2 blue M&Ms in a row? So we need to find the probability of a blue times the probability of a blue given that we've already drawn a blue. Well, the probability of blue, well, there is 1 blue out of the 18 possible outcomes. Whoops, I'm sorry. I can't see all of that. Okay, so it's gone. Whichever one of these is blue. Okay. Well, now there are only 17 M&Ms in the bag, but there are 0 blues. So this is 0. It's not possible. Okay, let's do some more practice. All right, so let's consider the 8 equally likely gender order combinations of a family with 3 kids. We've worked with this before. You can have either 3 girls, 2 girls, 1 girl, or no girls, and same thing with boys. Okay, so, and there are 8 possible outcomes. And it's implied that they are equally likely outcomes. Okay, so what is the probability that you get 3 boys? Well, the only one there is boy, 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 and there is one way for that to occur out of the 8 possible. Now, we can do this a different way. We can take that, if we have all the possible outcomes listed, we can just find 1 out of the 8 possible. But if we don't know, if we want the probability of a boy and a boy and a boy, again, these are independent events. So the outcome of one has no impact on the outcome of the others. So what's happening? So the probability that the first child is a boy is, you only have 2 choices. You have a boy or a girl, so it's 1/2. This has no impact on this, so the probability that the second child is a boy is still 1 out of the 2 possible genders. What happens with the third child has nothing to do with what happened on the first 2. So this is also 1/2. And if I multiply that out, I get 1/8. Okay. Let's see here. If I want to keep going. Yeah, I'll just keep going on with this. I think we can finish this up on one video. Okay, so in groups, consider the following experiment: rolling a fair 6-sided die 3 times in a row. Are these independent or dependent? They are independent. It is a fair die, so what happens on the first roll has no bearing on the other. Okay, so what is the probability of rolling an even number on all 3 rolls? So we're looking for the probability of even and even and even, which is the probability, since they are independent, of even times the probability of even times the probability of even. And if I remember back on my die, I can roll a 1, a 2, a 3, a 4, a 5, or a 6. An even number, there are 1, 2, 3 ways for that to occur, so 3 out of 6 is going to be 1/2. Okay, so the probability on the first one is 1/2. It is 1/2 on the second. It is 1/2 on the third. If I do my multiplication, that's 1 out of 8. Okay, number 9. Consider the following experiment: drawing a card from a standard deck of 52 cards, placing it on the table, and drawing another card from the deck. So what this means is this is without replacement. Those are dependent events. Okay. So the probability of the 2 events, this is going to be the probability of a king times the probability of a king given a king. Okay, well, if you have your standard deck of cards, you know that on your first pick, there are 4 kings out of 52 cards. But you've taken one out of there. You've taken a king out of there, which means there are only 51 cards left, and only 3 of them are kings, which gives you 12 out of, oops, and I did my multiplication wrong on that one. 2652. Which reduces to 1 and 221. Okay. All right, a couple more to consider. Consider the following situation. You're selecting people to serve on a 3-person committee from a pool of 10 men and 10 women. Okay. Okay. Are these independent or dependent? These are dependent. When someone is chosen, they would be removed from the pool. Now, you're not going to put them back in and choose them again. Okay. So what is the probability? And let's go ahead and that you selecting an all-male 3-person committee. Okay. Once again, if it helps you, I do this all the time. I'm going to do this. I'm going to write that there are 10 men. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And additionally, there are 10 women. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So, if we want to write our probability on this, the probability of a man and a man and a man is going to be the probability of a man times the probability of a man given you've already chosen a man, and times the probability of a man given man given, oops, man. Okay. All right, so we're going to start out. The probability of a man. Well, we have 10 out of 20 for our first draw, so it's gone. The probability that we draw a man, given we've already pulled a man out of there, well, there are only 9 men left out of the 19 people. So there's another one gone. Okay. Now, given that we've gotten rid of 2 men, or put them on the committee, I should say, there are only 8 men left, and there are only 18 left to select from. So once again, if you do that multiplication, this is 720 divided by 6840, which, believe it or not, reduces to 2 over 17. And our last problem. You've grown tired of M&Ms, so you've moved on to Skittles. A bag of Skittles has 12 red, 8 green, 6 yellow, and 3 orange. Okay. Once again, if you have any trouble with this, I'm going to draw them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Red, 8 green, 1, 2, 3, 4, 5, 6, 7, 8 green, 6 yellow, 1, 2, 3, 4, 5, 6, and finally 3 orange. 1, 2, 3. Okay, so if I total these all up, 6, 12, 24, 12, 20, 28, let's see, 6, 12, 18, 24, 25, 26, 27, 28, 29. Okay. All right, so there are 29. Okay. All righty. What is the probability? You choose a candy and you eat it. Okay, so this is without replacement. So these are dependent. Okay, so what is the probability that you choose a red, choose another red, and then a yellow? So we're looking at the probability of a red times the probability of a yellow given a red. Oops, I'm sorry, a red given a red times the probability of a yellow given red given red. Excuse me. Okay, so the probability of red, okay, there are 12 out of the 29. For the second red, one of them's gone, so there are only 28 left, and of those, only 11 of them are red. And for the yellow, now there are only 27 left, and there are 6 yellow. So that gives you 792 divided by 21,924, which is 22 out of 609. Okay. What is the probability that you choose all 3 orange? So we're going to look at the probability of orange times the probability of orange given you've already drawn an orange times the probability of an orange given that you've drawn an orange given that you've drawn an orange. Okay, so you have 3 out of 29 on your first. One of these is gone now, so you only have 2 orange left, but there are only 28 Skittles left in the bag. And lastly, you have 1 Skittle left, 1 orange out of the 27 Skittles left in the bag. That gives you 6 out of 21,924, which reduces to 1 over 3654. Okay, that was a long one. All right, we will start on part 2 here in a minute.